If you want to know how to turn a chemical name like this into an empirical formula like that, then this is the video for you. In the next 5 minutes, you'll learn how to write the empirical formula for common ionic compounds such as these. Let's go. Ionic compounds are one of the most common classes of substance that we encounter in chemistry. They form whenever a metallic element reacts with a non-metal. If a compound has a name like sodium chloride, that is a metal first and then a non-metal with an ending, say IDE, then you're looking at an ionic compound. And being able to work out the empirical formula for these compounds is a key skill that every chemist needs to know. Before I give you a shortcut to getting the right answer every time, let's quickly find out what's really going on and why the method works. Oh, and hang on until the end of the video and I'll give you a quick exam trick that can be useful if you get stuck. Ionic compounds form when electrons are transferred. Non-metallic elements gain electrons to fill spaces in their outer electron shells and reach a stable full shell configuration. We sometimes call this a noble gas configuration because that's what these elements already have. So, when a metal meets a non-metal, the non-metal atoms take the outer electrons away from the metal atoms, producing sets of charged ions. If you want to see this process in full detail, I have a separate video, which is linked here, but I'm going to show you the quick version of the process of how to use the dot and cross method to find the empirical formula of an ionic compound. So, let's say we need to find the empirical formula of the compound potassium chloride. We will start by writing the symbols of each element and putting their full electron configurations underneath. We will then use dots and crosses to show the outer electrons around each element, putting 1 dot next to potassium and 7 crosses next to chlorine. We then give each element its full electron shell by moving potassium's 1 outer electron across to chlorine. And this creates a pair of ions, with potassium having a 1+ charge and chlorine a 1-. As you can see, to achieve this stability, we only need 1 of each ion. And so our compound will have an equal number of potassium and chloride ions within it, and therefore an empirical formula of KCl. Here's a more complicated example involving aluminium and chlorine. As you can see, we now need 3 chlorines to take away aluminium's 3 electrons. And so we end up with an empirical formula of AlCl3. Notice that because the charges on the ions are the result of the electron transfer, they will always balance out to give us a compound that is neutral. This means that while this full formal approach will always work, there is a shortcut. Because we know the required number of electrons to transfer and the stable charges for many of the elements in the periodic table, if we learn some simple patterns, then we can write the empirical formula in seconds. For the elements that I'm showing here, the charges on their stable ions are very predictable. In group 1, they will all lose 1 electron to form 1+ ions. In group 2, they lose 2 electrons to form 2+ ions. Aluminium in group 3 will always lose 3 electrons to form a 3+ ion. Nitrogen and phosphorus in group 5 can take in 3 electrons to reach full shell electron configurations. And this of course will produce a 3- ion. Oxygen and sulfur in group 6 are only 2 electrons away from a full shell, and so will become 2- ions. And all of the elements in group 7 are only 1 electron away from gaining that full shell stability, and so will become 1- ions when they achieve it. At GCSE, these are the charges you will meet most often. And because the total positive and negative charges must balance, we can use this to write ionic compounds very quickly. Let's try potassium chloride again. First, we write the symbols K and Cl. And then let's just put their ionic charges next to them as superscripts. Because we can see that those charges balance out perfectly, we know that this compound's empirical formula will only require 1 of each ion, giving us a final result of KCl. Okay, let's do magnesium oxide in the same way. There's the Mg and the O. Magnesium ions have a 2+ charge, while oxide ions have a 2-. Once again, these charges balance out, and so our final empirical formula for magnesium oxide is just MgO. With magnesium chloride, we have this situation, and so we see we're going to need 2 chloride ions to balance out that 2+ charge on the magnesium. And the result is MgCl₂. Lithium oxide gives us a similar problem with a similar solution. In order to balance that minus charge on the oxygen, I will use 2 lithium 1+ ions and get a final empirical formula of Li2O. Try aluminium fluoride in this guided example. First, put the charges on your ions. Then, work out the numbers of them you'll need to achieve a neutral compound. And there you go. The basics covered in just a few minutes. Now, let's take this a bit further and prepare for the highest level exam questions. Sometimes we're faced with groups of non-metal elements that behave like a single ion. You only meet a few of these at GCSE, but you are expected to remember their names, their formulae, and their charges. Here they are now. There's hydroxide, carbonate, sulfate, and nitrate. At A level, you might also meet phosphate. Now, the good news is that these polyatomic ions work exactly the same as the single non-metal ions that we've already met. To write the chemical formula of potassium carbonate, I use exactly the same process that I've been doing so far. That is, I write the symbol for potassium and then the formula for carbonate. I add the charges, and then I balance out that compound by adding 2 potassiums for every 1 carbonate, and I get a final formula of K₂CO₃. If I'm faced with magnesium nitrate, you'll see straight away that I need to use 2 nitrate ions for every 1 magnesium ion in my compound. To make this clear, when I write it down, I simply put the nitrate ion in round brackets first, and then I add that subscript 2 at the end. Some elements have more than 1 stable ion, and chemists need a way to relay the information about which one they've got in the name of the compound. And in these situations, we rely upon Roman numerals to tell the reader what the charge will be on the metal ion. So you might see a compound written down like this, and we would say that that is copper-2 oxide when we read it out loud. The alternative would be this compound, which is called copper-1 oxide. Now, for those of you who like to know everything, those Roman numerals are actually telling us something called the oxidation state of the metal ion. But in these ionic compounds, that is just the formal charge on the metal ion. And so, to write down the formula of copper-2 oxide, we follow exactly the same procedure as before. First, writing down the symbols Cu and O, and then putting the charges in, which of course is a 2- for our oxide, and then we use that Roman numeral to put the charge on our copper ion, which in this case is going to be 2+. These charges balance out, and so we can see that our final compound's empirical formula will be CuO. What about copper-1 oxide? Well, it's the same symbols, Cu and O. The O still has a 2- charge on it, but the copper now only has a 1+ charge, and this means I'm going to need 2 copper ions for every 1 oxide ion, and the resulting empirical formula becomes Cu₂O. If you look at the formulae we've worked out so far, you might notice a relationship between the charges and the ratio of the ions. And this gives us a trick that will help you if you get really stuck in an exam. Let's say we've been asked to come up with the empirical formula of aluminium oxide. So, we're now going to try and balance out the 3+ on the aluminium with the 2- on the oxide ion. If we just cross those charges over, like this, we get the correct empirical formula of Al₂O₃. And that method will work for any pair of ions, but you must remember that the empirical formula must be the lowest possible whole number ratio of the ions. And so, if you use it for something like magnesium oxide, you'd end up with MgCl₂O₂. And you'd have to remember to simplify that to MgO, or you would lose marks in an exam. These shortcuts are useful, but remember that they are shortcuts, and they only work because of the electron transfers that are happening during ionic bonding. So please make sure you understand why those ions form, and not just how to use this method to combine them. That was a lot of new content in one go, so feel free to re-watch any section of this video. If you want to practice straight away, however, there's plenty of examples on this worksheet, which is also linked below for you to have a go at. Check your answers with the mark scheme and ask questions in the comments if you need any help at all. Remember that everything on this channel is free, because I believe that a good education should be available to everyone, everywhere in the world. So please, share this with a friend and help to spread the word.